Good afternoon. This is Ray Seifert. Today I intend to illustrate how to use arrays in Linux. So I will switch to using Eevee, and you won't see my pretty face too much more. All right. So I'm starting with an empty program and place a main program in here using the main icon on that toolbar, vertical toolbar on the right. So there I have a main program, and I'm going to alter it very slightly here. We use the frame command. Main has two parameters, and I will illustrate it with one local variable. I probably don't have much use for a local variable, but I'll do that anyway. And I will pretend that I have a function to call with two parameters. And I'll spend a couple of moments looking at how the frame command works. So clicking on the green alien, right, when it gets past the frame command doesn't generate any code. After that, it is able to display some data in a stack frame window. And you'll notice it says local 1. Now, for this to be completely correct, you need to subtract the variable frame size. And frame size is computed by the frame macro, and the code is searched by Eevee, and when it encounters the frame, it figures out whether it needs to show space for some parameters that have been stacked. So let's assume that we have a need for 7 parameters to the current function. Now when we get to the stack frame, all right, let's run this again. Subtract, and then it's correct. If we did have 7 parameters to this function, cur_par7 or current parameter 7 would be placed at RBP plus 6. If we had a need for 7 or more parameters for functions that we're going to call, then after the subtraction, you can see we have new par7, and this is located at RSP. If we had a need for 8 for call functions, then we have new par7 and new par8. And the reason why the new parameters are accessed using RSP is because you can have a hole in here. It keeps things on 16, keeps the stack on 16-byte boundaries, and with 2 parameters and 1 local variable, it had a need to put 1 more quad word on the stack, and that one is not currently labeled by anything. And if you were to try to address new par7 reference to RBP, it depends on how many parameters and whether local variables are on there. So it's just safer to use RSP and RSP plus 8. Alternatively, it's even safer to use RSP plus new par7. Likewise, for local variables, RBP plus local 1, and for parameters to the current function, RBP plus cur_par7. Now I'll revert it back to a more rational setup and start with what I really intended to do. And my goal for today is to illustrate arrays and I will create two arrays, A in the data segment. And to do this, I'm going to use times, not teams, but times 10. And I will put in this, how about data word 0. And I'll create another array in the BSS segment. And call it B. And with the BSS segment, the allocation is in terms of reserving. And for this, I'm making these word or 2-byte values and use reserve 10 to reserve space for 10 words on the stack. Now when we run the program, we see that we have 20 bytes displayed of A and 20 bytes displayed of B. And if we change the format to be decimal 2 bytes, we can now see 10 words. All right. So let's continue on, try to wipe out the highlighted line, and now let's write a fill function. And I'll fill this with random numbers. And again, I want to use a frame macro call for I'm not happy with the way that the completion facility works. All right, this frame macro, I'm going to use 2 for the number parameters, and we'll call it to fill. And I'll need 3 local variables, and I will call random, which has 1 parameter. So I need to subtract RSP comma frame size, and I will put in I can find where my cursor is. There it is. The ending to the function leave and return. All right. Now to call random, I need to use an extern statement. Extern random. All right. We have illustration here of the parameters for the function call. So we need to load the effective address of the array A. Oops, backwards here, into RDI. And after that, we need to move the number of words in A, so we'll move that into ESI and tell it there are 10 words, and then call fill. Let's see if I can get this to behave. So we'll call it twice, one with A and one time with B, and we will have our arrays created. All right. Now to use 3 local variables, I can name those local 1, local 2, and local 3 and just use them immediately as that. Alternatively, I can give them better names. I can say data, EQU for equate, and equate that to local 1, and then I can let N be EQU for local 2, and I want to have an I, which I'm going to use for a loop counter, equate that to local 3. So when I enter the function, I know I'm going to call random, and each time I call random, it's going to wipe out my registers, or probably will. So let's save these parameters, RBP plus data, RDI. That's the first parameter. And then move RBP plus N, RSI. And finally, we have a need for a loop counter. And I will use RCX, which is one of the parameters. Let's use ECX. Starting it at 0, and now we should be ready to do the body of the loop. And in the body of the loop, we're going to need to call random. But after we call random, we're going to have to restore ECX or RCX. So before we do that, we better save it. Move RBP plus random RCX. All right. Now, we're going to need to save the value of random every time we do this loop. And it turns out that we'll be fine if we start the loop here. So after we've called random, we have a random number in register RAX, and I want to use smaller numbers. So how about I do an AND operation, and RAX comma 0x 3FF. That will give us a 10-bit number. In order to put the data back into the array, we're going to need the address of the array, so I'll just load it back up where it came from in RDI, RBP plus data. And then we're ready to move into the RDI register, AX. So AX says a word register, but we need to either modify RDI or add in an index register each time that we do it. It will be more sensible to add in an index register, and the index register is RCX. Now, if we add it just like you see it, we're going to get RDI plus 2. We don't want that. 2 times RCX. Well, when you do this, the CPU will shift RCX by 1 before adding it to RDI. So there won't be any big loss of effectiveness by using an index register with a 2 times. It doesn't really require multiplication. Your choices are, you can use 1 times, but it's kind of pointless. You can use 2, 4, or 8. Anything else, you have to come up with a separate plan. Now we can increment ECX, and we can then determine whether we're ready to end the loop or not. And we should end the loop whenever RCX or ECX equals the value that was sent in as N, which was in register RSI. We can move it into the register, or we can compare it with the memory address. I suppose comparing with the memory address would be pretty effective. So let's compare RCX versus the memory address as RBP plus N. Now, when RCX equals N, we will have placed a location when RCX was 0, 1, 2, 3, all the way up to N minus 1, and that's going to be the last one. We don't want to put one in location 10 of the array because the array has size 10. We need locations 0 through 9. So we can do a jump equal, or we can do a jump greater than or equal. It doesn't really matter. I will choose equal because I'm pretty confident that I've got it right. If you have some doubt, it's safer to say GE because then you get out if you somehow manage to increment twice. But if you've done that, you got other problems. All right, so let's see if this will behave. All right, push RBP. And now the subtraction has occurred. So this is where RSP is located. We don't know the value of it without looking at the registers. But let's change the display of this to be 2-byte integers. And let's change the display of this one to be 2-byte integers. All right. Stepping forward, we've got RDI and ESI set, and it should be that RDI would be 602090. And if you look at the registers, RDI 602090. All right, now we're ready to call fill, so we use the step into button, which is the one where the arrow appears to go into the set of braces. Now we're in this function, and we're setting up the frame here, and you'll notice in the stack frame window we see data, N, and I, which is kind of convenient. If you've got several of them, it's handier to know what you're looking at. So now move RDI into the data position. You see 602090. Move RSI, 0xa is a 10, and then 0 out ECX, and we're going to, ooh, what did I do? What? Say there's a little echo. No, random doesn't need an I. I put okay, instead of random, I need I, yes. I put random in there. I was thinking about calling random and typed in random, I guess. I don't think somebody typed for me. Yes. I is a little better. All right, so I'll run it again, and this time I think I will have a bookmark there, or a breakpoint there, and tell it to go into the function. Here we are, and All right, so now we've got RCX set to 0, or almost. Now it's 0, and then we save it, and we see that I has a 0 value. Now we're ready to call random, and we get this crazy number, and the number with 3FF, and we get a 167 hex. Restore I is 0, and restore RDI, 602090. Then we're ready to move it, the AX value, into the array. So I'll switch to the data array, and it says this is showing it as individual bytes. So whatever that was is a 359. And says compare RCX with E plus N. Comparing it against 10, jump equal more, should have gone to more. It doesn't have the data there. See what we've got in these registers. RCX is this point a 1, and comparing it against RBP plus N, I don't know what's going on with the program. Oh, I got them backwards. Still shouldn't be equal. No, this is fine. All right, I'm going to do this again. And I think perhaps I've got problems with breakpoints. There's 3 of them or so in this program. Compare RCX, RBP plus N. Okay. I have 2 sets of eyes, my own and one more, watching me make these errors. Is there something I've done wrong with this jump equal more? Or is this comparison wrong? We'll take a little digression and inspect the list file. I'm not aware of the issue yet, but we see that RBP minus 16 is the correct location for the N. I'm going to take a wild guess and try putting minus 16, see if something is screwed up in my value for N. All right, data NI. After the comparison, we have the sign flag set. We do not have the 0 flag set. And let's see what it does this time. I'm taking a short break with this, trying to figure out what happened. And at the moment, man, why is my screen so bright? I haven't changed anything related to that. Gee. Is jump equal the correct instruction? I thought jump equal and jump 0 were the same thing. All right. It behaved exactly the same in GDB, which I took the time to investigate. And now return back to the screen sharing. Well, maybe I finally become less intelligent than I need to be. Oh, you've given me the clue. Thank you. Jump not equal. Trying all sorts of silliness. There was nothing with RBP plus N. It's like I must suspect that I've screwed up something more disastrous than my assembly code of the days. This reminds me of a tale from one of my good friends, Ronnie. And Ronnie told me this tale about his dad. He said when he was growing up, he used to work on his car a lot because cars back then didn't run like they do now. You had to change spark plugs and points and condensers fairly often. So he would come to his dad and say, "Dad, my car won't run." And he'd say, "Ronnie, what did you fix last?" And that was generally the answer. So that turns out to be what I have done. My most recent stuff is where I screwed up. Fairly common. Now, let's look at the assembly data. Change the format again to decimal format, 2 bytes, 359. Call random, we get another number. Let's go back to the registers. And we get 3C6 after doing the AND. And we restore I, it's a 1, that's good. Restore the data array, 602090 is correct. Move that into the register, into the memory location. Yeah, 966, that's probably correct. We can change it to hexadecimal if we want. 3C6. And then let's go back to the registers. Increment ECX. Be a little happier just to see the data, I suppose. All right, so we're filling up the array, running one instruction after another. I'm glad I don't have 20. 10's not too bad. All right, so now I've put 10 values into the array. We have RCX is an A, which is a 10. And now we're going to do the jump not equal to more, and you can see in the E flags here, ZF is set, so the comparison yielded a 0. Yes, we ended exactly the right point. And let's see, let's go back into main and fill the other array. All right, so it finished filling the 2 arrays, and now I want to have a third array. So I have a little use for this one local variable in main. Variable I'm going to call, heck, I can call it data. And what I want to do is to allocate an array and save the address of that array in data, which is a fairly common thing to do in C and probably fairly common in assembly language. I don't want all these breakpoints. All right. So after filling the array, then I want to call malloc. I have to tell it one parameter, the number of bytes to allocate. So I will tell it using EDI as the register. Let's tell it 1,000 locations or 2,000 bytes. Call malloc. After malloc returns, I'm not going to check the result, but it should return an address in RAX, and I want to save that onto the stack frame, RBP plus data, RAX. Now, with this code, RAX has the data array already in it. I want to call fill with that array, so I'm going to do that right now, but I'll do it more methodically. There's no real need to, but it's just a habit. Excuse me, I want to put the register in first, save it into RDI, and then tell it how many words I want to fill. 1,000, and then call fill. So, redefinition of data. It's not happy with me doing 2 equates with data. Let's change it to dot data. Dot data is a little bit different. It's a local label, and I don't have any other major labels here, so it's or global labels inside main, so there we are. Have to use extern on main on a random. excuse me, malloc. My brain is loosely connected. All right. All right, now we're off to the races. Fill A, fill B. Call malloc. I want to see the register first. And then we're going to move it into the .data location. And we have that value there. And now we're going to move it into RDI to be able to call fill. And we got 1,000 for RSI. And we can step into it, but it's going to be a little tedious. I believe I changed this. See if it's the right kind of defined variable. Oh, yeah. No, it's not. Let's cancel that one. All right. I thought I had changed that, but I hadn't gotten around to it. All right, let's wait until we've loaded RDI. And if I click on a value with a right click for a register, I've refined the way that I've done the definition of data for assembly language, and I'll call this one data. And I'll be defining an array that's going to go in this assembly data window, and I'll tell it to make the size 20 bytes, and I'll display it as hex 2. So now we have a third array here. So put the first word in there, increment ECX, jump to more, call random, and we're putting a second location value in, and let's put a breakpoint on that. So now we have completed filling 1,000 of them. I'm only displaying 10 of them to make it kind of convenient. All right. Next. And given the a very stupid sort. And the way to write something like this is probably to start with writing the C version of it as comment. So let's do that. C comment void sort. This was short star data int in. And I'll put the braces in. That doesn't really matter much. Inside the function, we want to have another integer for a loop counter, I guess. And see, I guess bool, I can't remember if that's in C or just C++. Sorted. And the way this works is sorted. And let's just do, how about do, wow, do some code and then while not sorted. We keep doing it while it's not sorted, and what we're going to do is bubble sort through the array, and we'll start by saying sorted equals false, and then we'll have a loop where we're going to go through, and I'll do it the easiest way possible. I'll just compare all the locations. For I equals 0, I less than n minus 1, we're going to compare location I against I plus 1. If data bracket I, and I want it in increasing order, so if data bracket I is greater than data I think we want this to be true at the start. I hadn't thought about bubble sort in a long time. If it's greater than data of I plus 1, then we need to switch things around. I think I will comment this as switch them or swap data. Because I don't really have to use a temp in assembly language, but I want to get the flavor for this code. And if you've made a swap, then the choice is to say that as far as we know, this is not sorted. All right. I believe that is an adequate version of bubble sort. So the first line, sort colon. And when we enter the function, we'll do push RVP. I don't want to push RVP in. Move RSP, comma RBP, oops, backwards. And we have two parameters in here. We don't really need local variables. We could put sorted and I into local variables, but there's really no need to. You can do it like this, there's nothing to call, or you can just say frame 2. And frame isn't all that important if you're not good thing in it, and the frame size is going to be 0, so this doesn't really matter either. All right. So now we need a variable for I and one for sorted, or registers for them. All right, so there we have it. So for this do loop, top there, so I know I'm going to go back to there. And for sorted equals true, about ECX, a 1. And now we have to translate a for loop. All right, if the for top is where we're going to go to at the beginning of the loop, and the variable for I is RCX, and we want to start with I equals 0, so we'll do XOR sorted. That's supposed to be D. This one matching my plan, ECX. And then at the top of the loop, we need to compare, and this will be a direct translation. We want to compare, is I less than N minus 1? N is in register RSI. It'd be effective to just use ESI. So if I want to compare it against N minus 1 and I don't need N any further, then I can decrement ESI. The compare then is going to be I, which is ECX versus ESI. And as long as it's less than, we want to do the body of the loop. If you want to make an easy translation, jump not less than is to jump to the end of the for. Name it for end. All right, that's the easiest way to do it. Jump not less than. You see less than in the comment, so jump not less than. Next, we're ready to translate this if. I guess I should put the for end in here. Now translate the if. We can't compare a memory location versus a memory location, so we need to move one of them into a register. And if we're going to swap, we'll have to move two of them into a register. So let's do both of them. And if we go back up to the top of the program, we can see in these comments that were drug in that the registers that are used for parameters, two of them were registers used for that function, two of them I've used so far, and I've got two more. I'll use R8 and R9 for my two registers for the values to extract from the array. Let's see, R8 word, because we got a word size array, and we want to get the array from RDI plus 2 times RCX, and that will get us one of them. And for the other one, we want to move into R9W. And syntax is about the same. And I believe we'll be able to add a 2. It'll go in as part of the field that is there. Let's see if this works. All right, so I guess it is the numeric field or constant field. We've got the two of them in there. And now compare R8W and R9W. I can say R9W, and occasionally I can type it. So if we have them out of order, then we want to skip the swap. So we want to jump not greater than to no swap. All right, so in this section right after this, we want to swap them. And to swap them, we just want to move these values into the locations that we just used. Oh, I put RSI. Did I say RSI in addition to typing RSI? RDI, I'm going to use the array as the first parameter. And we loaded from 2 times RCX into R8, so we want to put R9W in there. So the swap is just moving them. And at this point, I should be ready for the no swap. I lost a little bit. All right, jump not less than. This label here should be no swap. Now, when we do the update part of the loop, one other thing to do if you have to swap is to set sorted equals false. Sorted was register RDI, so we'll move XOR would be a good choice there. EDX, comma EDX. I'm going to shift this over a little bit. All right, so now it says sorted's false. We're in this for loop, and before we get back to the top of the loop, we need to increment ECX. I think that's the one I'm using for I, and then jump for top. I might have this coded correctly at this point. It's kind of hard to know. Let's see what happens. And let's try sorting A first. Come on. All right, so instead of calling fill, I want to call sort. And let's see how well I've done here. Change it to decimals 2 bytes. Step into the sort function. Let's check the registers here. EDX has a 1, yes. Loop counter is 0. Decrement RSI, that's going to be the number to check against for n minus 1. Compare them. So we're going to do the body of the loop. I don't know if I checked to see. I didn't do while not sorted. Well, let's see what happens with this code when we execute this. Well, it looks like it's capable of doing the bubbling, but without the while not sorted implemented correctly, it's not going to finish. All right, so it'll keep testing forever after it sorts the data. So while not sorted is going to become compare EDX. Let's see, versus 0. So if it's sorted, EDX is going to be a 1. And let's compare it against 1. So jump. If it's sorted, jump not equal to I think I called that one top. All right, let's see how it behaves now. All right. Got a 1 for sorted, 0 for ECX, decrement, that gives us n, or n minus 1, which is 9. Compare them, and we're in the for loop. All right, so we're swapping the second pair. I think I want to figure out why it didn't swap the first pair. Oh, it did. All right, so 966 is the first pair of them. Let's see. ECX is now at 9. We jump to 4 top, and we compare them, jump not less than there. So now we compare EDX versus 1, and it's not equal, so we go back to the loop. All right, so it looks like we've done the test correctly, I'm going to switch back to the data and watch the numbers as it moves the 359 forward into the array. All right. So it finished with the 809 in the second position, and now we're going to end up with a 359 in the third position, counting from the top. And then the 255 is going to be in its final position, then the 236, then the 205, and I'm wasting time. I don't know where we're at, but it sorted the array. It's a miracle. Sort. And let's sort the B array. All right. Evans. We just watched it sort A. So it's dying inside sort. So let's see what the heck happens at the end of that function. Got our numbers in there. Step into the sort function. Did I put leave return in there? I wonder. Oh, so when it didn't jump on not equal to top, it just ran off the end of my program. Let's try again. Field A, sort A, field B, sort B, allocate data, fill data, and sort data. Well, I used a poor choice of data values with 1,000 entries in an array, and all of my entries are between 0 and 1023. I don't have very interesting numbers. After sorting, it's 0, 1s, and 2, 3s, and 5s. Didn't get a 4 though. All right. Thank you for your assistance, Carson. I was confused, and who knows how long confusion will last when you're looking in the wrong place for the solution. I think that's enough for today, and I'm going to tell this thing to stop the broadcast.